About essentially looking at why rotation takes place. Essentially, I was only focusing on things that are just rotating and not translating, and so-called what I would say pure rotation problems. You're just looking at the rotation of different objects. You're not really interested in how they move from here to there. And we started off by these definitions for a point particle. For a point particle, it is true that if you define a vector which is r cross f, f being the net force on that particle, and then you define another vector which is the angular momentum r cross p, then if you apply this to a collection of point particles in the context of an object rotating about some axis, so for example you have this object that is rotating about this axis that is passing through point O, if you apply these definitions for a point particle to an object that is rotating about this axis, you chop up this object of course into little pieces, apply those to each little piece, and you find that the total external torque acting on this object must be equal to the moment of inertia of this object about this axis times the angular acceleration, where I have taken by convention the z-axis to be pointing out of the board. Okay, and we did one. So notice on the left hand side you have the net external torque, which is good because the external torque is something that you can calculate. The internal torques are not something that you can easily calculate because you don't know the internal forces. I is the moment of inertia and alpha is the angular acceleration about the axis of rotation. Okay. Watch closely because this is one of those chapters in which the mathematics itself is relatively straightforward, but the physics part is more troublesome, and whenever the physics part is more troublesome, then of course there are more words that I have to speak out loud to explain what I am doing and why I am doing it. Okay, you cannot fall back on equations so much because there are fewer equations to begin with. Okay, anyway, how to get help in Windows? I don't need that. Okay, ये Bing है, usual Bing nonsense. Okay, अच्छा चलो कोई बात नहीं, इसके बाद तो होपफुली कुछ नहीं होगा. Okay, तो इसमें कोई लाइट डिटेक्टर है मॉनिटर में है. Okay, स्मार्ट मॉनिटर. Okay, मशीन लर्निंग का आ रहा है मॉनिटर. Okay, कह रहा अंधेरे में मैं आ गया हूँ इसलिए you need help. Okay, anyway, so you have essentially I gave you one very simple example that if you have a ring which is essentially there are some light spokes for this ring, and the ring can just rotate about this point. So you have nailed the ring to the wall, for example, over here. So the ring can just rotate about this axis, whether clockwise or anti-clockwise. That depends on how the force is applied. So if you wrap some thread around this ring and pull this ring with some force F, okay, the total torque acting on this ring about this axis, if the radius of the ring is capital R, I'm sorry over here by the way, many people do use capital R for the radius, of course. It's dangerous to use small r because of course there's the position vector coming along as well very often, and r you are using for the position vector as well. So you use a small r without the arrow, then you have the possible confusion with the magnitude of that r vector. Unfortunately, very soon we also have to deal with the center of mass. So it turns out that if something is both translating and rotating, the easiest way to analyze that motion is to analyze it as, well, that there's angular momentum due to the motion of the center of mass, and then there's angular momentum because of the motion around the center of mass. So very soon capital R vector will also be appearing. So then there's a possible chance of confusion with this radius. So it's a good practice you use some other radius symbol for the radius. In other words, typically people use small b. Okay, तो अगर आप देखो radius, if you want to be very safe, radius को typically आप small b से denote कर सकते हो so that you don't confuse it with the other r's that are floating around in this problem. Okay, anyway, so in this lecture, if you see b somewhere, that's going to be some radius. Okay. Anyway, in this case, since we haven't talked about the center of mass yet, let's just stick with capital R. What's the torque or about this axis? How do you find that out? Again, you draw a vector that joins the point about which you are calculating the torque. And why are we calculating the torque about this point? क्योंकि इस गिर्द के नहीं, because इस गिर्द के गिर्द रोटेट कर रहे हैं. अगर किसी और पॉइंट के गिर्द अगर आपने नेल किया होता उस पॉइंट के गिर्द रोटेट कर, then you would have calculated torque about that point. This is a pure rotation problem. You don't need to worry about the center of mass. You just need to worry about the point about which the object is just rotating. Okay. So in this case, this point happens to be the center of mass, but it need not be the case. Okay. In this case, so you draw a vector like that joins the point about which you are calculating torque to the line of action of the force. Any choice of R will do. You can choose this R as well, but then of course that is needlessly more complicated because then you have to take into account this angle. What will go into the cross product, of course, is the magnitude of this vector times the sine of this angle, which again gives you this much length. So you might as well choose this vector R such that is perpendicular to the line of action of the force. Okay, so in that case, then you just get that R cross F का direction क्या होगा? Is it into or out? So you do first of all R को उधर slide करो और फिर आपका आ जाएगा ये R है, ये आपका F नीचे की तरफ है, so you have the thumb pointing into. Okay, so this is basically equal to capital R times F minus EZ. कोई और भी ले सकते थे, you would have gotten the same result, क्योंकि वो कोई और लेते, अगर आप ये ले लेते R, तो फिर आपका आ जाता कि भाई इसकी length times the sine of the angle of sine of this angle times F, but इसकी length times sine of this angle equals this length, the radius. So you would have gotten exactly the same result. Okay, and this equals I times alpha EZ. The sine is just telling you that angular acceleration will be into the board, which just implies in this context that the thing is going to rotate clockwise. Okay, so essentially because क्यों clockwise? क्योंकि as time goes on, theta is decreasing then. Remember हमने किस तरह एंगल को डिफाइन किया था, ये आपका थीटा है. अगर थीटा इंक्रीज कर रहा है तो कैसे इंक्रीज करेगा? एंटी क्लॉकवाइज. सो एंटी क्लॉकवाइज rotations correspond to positive signs, clockwise rotations correspond to negative signs. Okay, so alpha being negative means कि ये angular acceleration इसकी clockwise है essentially. So this force will tend to rotate this thing clockwise. Of course it does. I mean, it's physically obvious that this thing will rotate clockwise. Okay, and therefore alpha, I'm not just worried about the magnitude of the angular acceleration, which is F times R divided by I. And for this ring, since the masses of the spokes are assumed to be negligible, for this ring, the moment of inertia, if you recall, the moment of inertia is basically a sum. Okay, not this sum, some other sum. Okay, the moment of inertia is a sum. Oh God, ये तो ज़्यादा. जैसे जैसे सेमेस्टर खत्म होता जा रहा है, इन्होंने जो बिजनेस स्कूल वालों ने WD-40 जो डाला हुआ है वो सूखता जा रहा है. Okay, but anyway, okay. So you have essentially, so the moment of inertia, if you remember, is a sum. As in, for the object, you chop up the object into small pieces. The mass of each piece multiplied by the distance squared of the piece from the axis of rotation. When I say distance squared, I mean the perpendicular distance squared from the axis of rotation. क्या चीज? Negative जो show कर रहा है कि ये clockwise rotate करेगा. किधर? Yeah, मैं कहा था कि now I'm just worried about the magnitudes. So never mind the minus sign. Minus sign तो बता रहे clockwise है, मुझे पता चल गया. Now I'm just worried about कितनी तेजी से clockwise. Okay, so that's why I just threw away the negative sign. Okay, right. So the moment of inertia in this case will be, because each piece of the ring is the same distance away from the axis of rotation, which is capital R. This R I square is just capital R square for each and every piece in our case. And therefore this r square you can take outside. What is left is of course the total mass of the ring, which is just equal to, gives you mr square. You plug this in and you find that alpha in this case is just fr over mr square, which gives you f over mr. The smaller the radius of the ring, the faster the angular acceleration, the more quickly it will start to rotate. Of the boat plus Majnu system just after the jump. Just after the jump, it's mu cos theta minus mv, where v is the speed of the boat just after the jump. And you know, anybody can solve this one. This is just mu cos theta over capital M. Again, make sure that your answer makes sense. The faster that Majnu jumps, the more the recoil speed of the boat. The heavier the boat, the smaller the recoil speed of the boat. Again, that makes sense. Okay? Right? Again, you know, now we were, again, as you see, you can be able to make a precise quantitative prediction, even though we didn't know the force with which Majnu jumped. We just knew the total effect of that force. That once Majnu lost contact with the boat, this was the speed of Majnu just after he lost contact with the boat. That's the only thing that we know. Okay, so you're not really interested over here in what the force is, you just really use the effect of that force instead. Okay, and this is a quantity much easier to measure compared to the force that Majnu exerted on a boat and vice versa. Okay, so Majnu is in the air. Once Majnu is flying through the air, is the momentum of Majnu constant? No, of course not. The vertical momentum of Majnu is changing. There is a net external vertical force on Majnu, right? The horizontal momentum of Majnu remains constant. Why? Because there is no horizontal force acting on Majnu. That's simple projectile motion essentially once Majnu is in the air. Okay. The momentum of the boat, does it change once Majnu is flying through the air? No. The momentum of the boat is purely horizontal, and therefore you need a horizontal force acting on the boat to change the momentum of the boat. Is neglecting any drag forces being exerted by the water on the boat, there is no such force. So therefore the boat keeps on moving to the left with the same speed v. Now imagine, you know, I'm now approaching, you know, our territory from PG-13. So now Majnu has landed over here, and you know, before it proceeds further, cut. Okay, so Majnu has landed over here, and that's where it stops. Okay, if you want to see the story continue, then enroll in the humanities course. Okay, but anyway, okay. So Majnu essentially has landed over here. Once he lands on the beach, and before he does anything else, what's the momentum of Majnu just after he lands on the beach? Zero. Of course, he's stationary with respect to the ground. I mean, cut. Okay, uske baad we don't care. Okay. Anyway, okay. So what's then the momentum of the boat at the instant when Majnu comes to a stop on the beach? Of course, the boat keeps on moving. So why isn't the momentum of the boat plus Majnu system, why isn't the horizontal momentum of the system being conserved now? अब system का तो momentum change हो गया horizontally. Initially, जब मजनू जो jump भी नहीं लगाया था, उसका system का momentum 0 था. Now the system does have some momentum horizontally. मजनू रुक गया है, boat आप कह रहे हो, अभी भी move कर रही है, so of course. Exactly. There was an external force that acted on Majnu in the horizontal direction. Initially, Majnu has some horizontal momentum pointing that way just before he makes contact with the beach. And therefore, the ground exerts a force in that direction horizontally to bring him to a stop. The ground also exerts a big force upward as well, bigger than the weight of Majnu, much bigger than the weight of Majnu, because Majnu is also traveling vertically downwards. Ground में उसको रोकना भी तो है. I mean, just take a weight machine, उसके ऊपर jump लगाओ. Just after you land, आपको बड़ी अचानक spike नजर आएगा reading में, and then you know very quickly it goes back to your normal जो भी आपका weight है. Okay, simply वो reading क्यों ज़्यादा हुई है? Simply because the surface of the weight scale. What is the weight scale measuring? It's essentially measuring the normal force that you are exerting on that weight scale. वो आपका weight नहीं measure कर रहा होता असल में. You are measuring the weight indirectly when you stand on a weight machine. It's actually the weight machine is only measuring the force that you are exerting on the weight machine. वो essentially छोटे जो springs लगे हुए हैं, there are different mechanism of course to do it, but a very simple weight machine would be कि छोटे जो springs लगे हुए हैं, वो essentially the weight machine measures कि भाई कितने spring compress हुए हैं, and basically क्यों compress हुए हैं, that's because of the force that you are exerting on the weight machine.
Sir, मजनू land होते ही लगभग थोड़ी जाएगा, थोड़ा roll
Well, I mean, depend करता है. I mean, उसके वो if he digs in his heels तो तकरीबन instantaneous. I mean, the time of collision, the time duration of the collision, of course, is variable. Okay, so उसी वक्त instantaneous is an extreme approximation. But even if it takes a finite time, 0.1 seconds, 0.5 seconds, right? The point being कि horizontal momentum नहीं conserve होगा. Okay? नहीं jump बड़ी है या छोटी है या जो भी हो गया है, वो तो ही ना. क्या ही नहीं हिलोगे of course, but the question is in typical physics fashion is that what we are primarily interested in is not Majnu and what happens to Laila, okay? What we are interested in is को भूल जाओ उन सब चीजों को, boat को क्या हो रहा है, okay? So तो boat को essentially the boat gets a recoil velocity and then it keeps on moving in the same velocity if there is no other force, okay? आपने छलांग जिस तरह मारी है, आपकी छलांग का इफेक्ट आ रहा है इधर U में, जोर से छलांग मारोगे U की ज्यादा वैल्यू होगी. आपकी डायरेक्शन जिस डायरेक्शन में हमने छलांग मारा है, दैट इज आल्सो अफेक्टिंग द स्पीड ऑफ द बोट. सो इफेक्ट हो रहा है. ऑफ कोर्स इट आल्सो डिपेंड्स ऑन द बोट का क्या मैस है. अगर बोट का बहुत ज्यादा मैस है, बिल्डिंग से छलांग मारते हो क्यों नहीं बिल्डिंग रिकॉइल करती है. मसला ये है कि वो पैराशूट के साथ भी प्रॉब्लम नहीं लगा सकते, क्योंकि पैराशूट जब तक खोलोगे तब तक पहले से फ्लैट हो चुकी होगी. बट एनीवे, ओके. Right, so again, it's very important. It seems a trivial point when you're reading about it, but it's very important to keep in mind कि आपका system है क्या. Always remember over here I was treating, once I defined my system to be Majnu plus the boat, I always had to treat it like that. I cannot midway through the calculation consider the beach to be part of the system as well. Then if I can do that, but then I have to go back to the first step.
Sir, system जो है वो breakdown नहीं होगा क्योंकि दोनों इतने दूर हो गए.
It's up to you to define the system. Doesn't matter कि वो linked हो. You can have a system of non-interacting particles. There doesn't even need to be a force between the two particles that you're considering part of your system. In that case, the internal force is zero.
The center of mass अभी भी उसी position पे रहेगा.
हाँ, अगर internal force zero है, okay, right? क्योंकि we remember if the initial momentum of the system is zero, then the center of mass initially is not moving. And then if there were only internal forces acting, then the center of mass remains put. It cannot move. Okay, so let's do another problem, the classic problem. The red spot problem, I call it. A collision, simple head-on collision. So you have essentially a particle of mass m1 moving speed u1, another particle of mass m2 moving speed u2. And this is before the collision, and this is after the collision. After the collision, again you have mass m1, this is v1, mass m2 moving with speed v2. If I consider that this is a perfectly, if I have this collision, I consider that is my direction of my x-axis, then I can write down that the momentum of particle 1 is simply m1 u1 ex plus m2 u2 ex. Right? Again, notice that u1, if it's negative, just implies that this particle is moving to the left. If u2 is negative, that just means that this particle is moving to the left. So you can see from here that the signs of u1 and u2 are telling you about the direction of motion, because if u1 is negative, you can consider that negative sign to be multiplying ex, so that the direction of motion becomes negative ex. So this is m1 v1 ex plus m2 v2 ex. And then of course, the shorthand form of this is you just write it without the unit vectors. So you just get the equation that you can see in red spot. Okay, so this must be familiar to you, okay, because this is, अगर आपको 3 महीने पहले पूछता, आप कोट भी कर सकते थे किस पास पेपर में इस किस्म की इक्वेशन आपको नजर आई है, okay, June 2012 probably or whatever, okay, but anyway, okay, and then if this is a perfectly elastic collision, what does that mean? That just means that, as the name implies, it's a very, very springy collision. Essentially, the surfaces, when the two particles collide, the surfaces deform, but then the surfaces bounce back. just like a spring. That just implies that there was a conversion of the initial kinetic energy of the two particles into elastic potential energy, and then when the surfaces bounced back, that elastic potential energy was converted back to kinetic energy. There is no other energy that you could convert to. Yes, there might be some acoustic energy, there might be some, maybe if these are very good spark वगैरह produce होता है, negligible amount of light energy or something like that. Those are negligible normally, okay. So it's basically that to a very good approximation, if this is a springy collision, the kinetic energy is conserved. If you're playing billiards or pool, again, to a very good approximation, you're dealing with elastic collisions. Why? कैसे एक collision को देख के, सिर्फ देख के, if I give you a video of a collision, how can you decide, just looking at that video, whether to a good approximation, whether the collision was elastic or inelastic, the opposite of elastic being inelastic, okay. Most collisions are somewhere in between. They are mostly elastic or mostly inelastic or maybe half elastic, half inelastic, something like that. But how can you say from a video that, okay, to a very good approximation, this collision looks like an elastic collision? I said just looking at a collision. ChatGPT कई दफ़ा बहुत stupid answer दे रही होती है, okay. नहीं, वो external forces तो आप इस्तेमाल करोगे ना, तो analyze के होता क्या उसके बाद. Just by looking at the video. वो तो inelastic collision में भी हो सकता है. नहीं, आपने कोई measurements नहीं करनी. आपने सिर्फ वीडियो को देखना है. It's much simpler than that. जैसे मैंने बताया, आप बेसिकली स्लो मोशन में देखो कि सर्फेसिस को क्या हुआ है. वो जो टक्कर हुई है, वो जो सर्फेसिस एक दूसरे के साथ टकराई हैं, उनको क्या हुआ है. उन्होंने अगर शेप चेंज की है, दो केसेस हो सकते हैं. या तो उनकी शेप एप्रिशिएबली चेंज हुई है, जैसे हमने गाड़ी दरख्त में मारी है, आपकी गाड़ी के फ्रंट की एप्रिशिएबली शेप चेंज होगी. अगर आपने बिलियर्ड बॉल मारा है दूसरे बिलियर्ड बॉल की तरफ, उसकी शेप नहीं चेंज होती होपफुली, अदरवाइज बड़े फुस किस्म का सेट लिया आपने, ओके. सो वो शेप नहीं चेंज होती. That immediately implies that to a very good approximation, this is an elastic collision. क्योंकि essentially वो kinetic energy देखो किस form of energy में फिर convert हो सकती है after the collision. किसी भी और form में convert हो सकती है. There was no conversion of the kinetic energy to elastic potential energy to begin with. कोई surfaces deform ही नहीं हुई तो elastic potential energy कैसे store होगी? When there was no conversion of kinetic energy to elastic potential energy to begin with, वो kinetic energy में रह जाती है सारी energy. There is no other possible energy that it could transform to. Internal energy में तो फिर इसलिए transform होती है कि वो surfaces deform करती हैं और फिर वापस surfaces नहीं आती अपनी original shape की तरफ. Then all that energy is essentially absorbed into the energy of the atoms and molecules of the colliding objects, into the internal energy. फिर मोमेंटम नहीं कंजर्व होगा, राइट. फिर तो मोमेंटम ही नहीं कंजर्व होता. इधर वी आर टॉकिंग अबाउट द कंजर्वेशन ऑफ काइनेटिक एनर्जी. सो व्हेन यू से द कोलिजन इज इलास्टिक, यू आर टॉकिंग अबाउट द कंजर्वेशन ऑफ काइनेटिक एनर्जी. ऑफ कोर्स एनर्जी इज कंजर्व्ड, बट द इशू नाउ इज काइनेटिक एनर्जी कंजर्व्ड. वो यस फॉर एन इलास्टिक कोलिजन, यस. ऑल्दो यू नो ज्यादातर क्लास का नहीं पता क्योंकि उन्होंने 1980s के पास पेपर नहीं सॉल्व किए थे. सो दैट्स वन वे टू टेल कि अगर आपके कोलाइडिंग ऑब्जेक्ट के सर्फेसेस इन डिफॉर्म है. So now you can immediately say कि अगर आपका दो गाड़ियों की टक्कर हुई है, that's not an elastic collision, because you know dent पड़ती हैं और वो जान के पड़ती हैं. It's not to do with build quality and stuff like that. जब आपकी गाड़ी टक्कर हो, it's designed such that it's an inelastic collision, ताकि जब कोलाइडिंग आपकी गाड़ी टक्कर हुई है दो गाड़ियों की, अगर उसके बाद भी कोई काइनेटिक एनर्जी ढेर सारी बच गई है, क्या होगा इन गाड़ियों को? Will bounce back, and then what's the corresponding change in momentum? Suppose that this car was traveling at a high speed and came to a stop. ठीक है, there is a big change in momentum that the driver experienced, so there was a big force on the driver. But it's far worse अगर एक driver साहब initially इस तरफ जा रहे हैं and then after some time he goes in that direction. Then that's a much bigger change in momentum. और then the driver जो शायद पहले बच जाता है, उसके अब जरूर ही गर्दन डिसलोकेट हुई पर ही होगी when he experiences such a big force. तो जब वो गाड़ी को जो है ना वो जब क्रम्पल अप करती है, दैट्स जस्ट ए कॉम्प्रोमाइज कि चलो गाड़ी तबाह हो जाए, आपकी जान बच जाए. ओके ओके. सो व्हाट्स द अदर वे? इफ यू सी अ वीडियो दैट यू कैन सी दैट इलास्टिक कोलिजन, जस्ट लाइक एक ब्लॉक है, उसको मैंने स्लाइड किया है टुवर्ड्स ए स्प्रिंग अटैच्ड टू ए ब्लॉक. दिस ब्लॉक ऑफ कोर्स इन सम सेंस कोलाइड्स विद दिस थिंग, But this is an elastic collision. When this is one object, when this object hits this object, the surface of this object gets deformed. Surface is case में literally spring. But then as this block compresses, रुक जाता है, ये भी कुछ कर रहा होता है आगे, and then the spring goes back to its initial position, and then essentially this block bounces back. आपकी कोई भी surfaces की shape change नहीं हुई overall. So therefore this is an elastic collision. That's what I mean by springy collision. It's there in the name, elastic. इधर से नाम आया. That is a very springy kind of collision, okay? Okay. So assuming that this is such an elastic collision, in the recitations you'll probably see, not in this week, क्योंकि इस week मुझे पता है midterm के नशा चढ़ा हुआ है आपको. Next week you'll see inelastic collisions. Inelastic collisions are relatively easier to analyze. Elastic collisions, it involves slightly more mathematics. So if you assume that this is an elastic collision, the total kinetic energy remains the same. So you have half m1 u1 square plus half m2 u2 square equals half m1 v1 square plus half m2 v2 square. So this is a perfectly elastic collision. Okay. If you just had conservation of momentum, which of course is true in this case because you are treating both your colliding objects as your system, and during the collision they only exert internal forces on each other, you are ignoring any friction between these objects and the surface on which they are sliding. So there is the weight, there are external forces acting over here, but the net external force is 0. There is the weight, but then there is also the normal forces, and in this case the normal forces equal the weight, and therefore the net external force is 0, so momentum is conserved. Assuming an elastic collision, the kinetic energy is conserved. The objective now, if you just had this, the objective would have been figure out V1 and V2, given the values of M1 and M2 and U1 and U2. You could be the world's smartest mathematician, but you would not have been able to find out V1 as a function of M1, M2 and U1 and U2 if you only had this equation. If you were the smartest mathematician, you would have realized that that's a futile task to begin with, okay, because you just have one equation and two unknowns, okay. So that's a bit of an oxymoron, okay, but anyway. You now, assuming a perfectly elastic collision, you also have the second equation. But this equation is quite troublesome, okay. Why? Because this is a non-linear equation. The things that you want don't come with power 1. V1 and V2 are what you want. The V1 and V2 tells you about what happens to the objects after the collision. But those come with power 2. These are non-linear. This is a non-linear equation. This is a linear equation. This is a non-linear equation. It's always much easier to solve two linear equations. इसलिए आपने grade 7 में simultaneous linear equations की थी. You didn't do simultaneous non-linear equations, okay? Right? Now the objective now is that you can tidy this up. The strategy is generally that you tidy this up, combine this equation with this equation to get an effective second linear equation, and then solve this linear equation with the second effective linear equation. You solve those two simultaneously. That's essentially how you will get V1 and V2 in very simple terms. Okay. So let's actually carry that out. This second conservation of kinetic energy, aka elastic collision, equation can be written as m1 u1 square plus m2 u2 square. Of course, all I'm doing is to multiply by 2 throughout. m1 v1 square plus m2 v2 square. And then you'll see this over and over again. The idea is just to tidy this up by bringing terms that contain m1 to one side, terms that contain m2 to the other side. So if you do that, you get m1 times u1 square minus v1 square equals to m2 times v2 square minus u2 square. And now you use the only thing that you remember from grade 8, which is a square minus b square is equal to a minus b times a plus b. And you get that this is u1 minus v1, u1 plus v1 equals u2 equals m2, v2 minus u2, v2 plus u2. This looks very, very similar to your conservation of momentum equation. Because if you write down the conservation of momentum equation, what do you see? Let me rewrite it in another way. Again, to the conservation of momentum equation, aka this, I do the same thing. I bring the terms that contain m1 to one side, I bring the terms that contain m2 to the other side. If I do that over here, This, remember, is not conservation of momentum. This is conservation of kinetic energy. If I do the same thing over here, I get m1 times u1 minus v1, because this m1 v1 goes to the left, m2 u2 goes to the right, and I get m2 times v2 minus u2. This is, of course, nothing other than conservation of momentum. This is, of course, nothing other than conservation of kinetic energy. But now if I divide this equation by that equation, what do you see? This looks very, very similar to that equation. It's just off by some amount, okay? If you divide this, the left-hand side, by the left-hand side of this equation, what do you get? m1 is the same, u1 minus v1 is the same, all you're left with is u1 plus v1. And similarly on the right-hand side, all that is left is u2 plus v2. So this would be very easy for you to memorize, okay? You don't need to memorize it in this course, but you know, since you are so fond of these mnemonic devices to memorize stuff, okay, in physics, okay? This is very easy to memorize, okay? Physically, what is this thing telling you? Physically, this is telling you that u1 minus u2 equals v2 minus v1. What is this thing telling you? Or in other words, let me write in the opposite way. u2 minus u1 equals equals minus. Let me write it with a minus. u2 yeah, okay. What is this thing telling you? But what is this thing telling you physically? The relative velocity before the collision of the two objects equals in magnitude the relative velocity of the objects after the collision. The relative velocity of the objects after the collision is just opposite in direction. That's what this minus sign is telling you. u2 minus u1 is the relative velocity between the two objects before the collision. I mean, अगर ये जा रहा होता 60 kilometers per hour और ये जा रहा होता 120 kilometers per hour, what would you have told me for the relative velocity? 120 minus 60. इसलिए मैं कह रहा हूँ u2 minus u1 is the relative velocity. इसमें कोई इतने घूर के देखने की जरूरत नहीं है, okay? By exactly the same reason, v2 minus v1 is the relative velocity after the collision. Of course, I'm not bothering about relative velocity according to who of what, because I'm really interested in the magnitudes, okay? This is the relative velocity of object 2 according to 1, I think, okay? So you have that. And then it's flipped because of this minus sign, okay? Anyway, so this gives you the physical meaning that in an elastic collision, the relative velocity before the collision equals in magnitude the relative velocity after the collision. So what people do is, okay, ये है perfectly elastic collision के लिए. Let's say if you had a perfectly inelastic collision, what's the relative velocity after the collision? The two particles stick together for a perfectly inelastic collision. So they both move with the same velocity. What's the relative velocity then after the collision for an inelastic collision? 0. Because both particles after the collision are moving with the same velocity with respect to the ground. So with respect to each other, they are moving with the velocity 0. So therefore, वो कहते हैं realistic collision में इधर एक coefficient डाल देते हैं R, which tells you कि अगर R 1 है, then this is a perfectly elastic collision. अगर R 0 है, then you are dealing with essentially an inelastic collision. And this R is what is called the coefficient of restitution. Okay, essentially that's the idea behind the coefficient of restitution. In one of the problems in the readings, you look at this, okay, but anyway, not important, okay, over here, but I just wanted to point that out क्योंकि किसी ने जिक्र किया था coefficient of restitution. It basically tells you essentially how elastic or how inelastic the collision is. For elastic collision, this equation is perfectly obeyed. If this is not perfectly obeyed, as in the right hand side becomes smaller than the left hand side, the coefficient of restitution takes into account how much smaller does it become. Okay. So anyway, now you have another equation. This is the product of, this takes into account conservation of kinetic energy. Therefore, it's much easier to solve this equation and this one. These are now both linear equations. You can solve these two simultaneously. It's much harder to solve these two simultaneously, but using these two, you can produce another linear equation, and then solve the original original linear equation and this new second linear equation that you've derived. Okay. If you do that, then you first of all you say, okay, V2 from here, V2 is equal to U1 plus V1 minus U2, and then you plug this into your conservation of momentum equation, and you get M1 U1 plus M2 U2 equals to M1 V1 plus you have M2 times V2, and you get U1 plus V1 minus U2. And remember, your objective now is to figure out V1. Then this equation does not contain V2, it only contains V1. So you just solve for that. So you get M1 U1 plus M2 U2 equals M1 V1 plus M2 U1 plus M2 V1 minus M2 U2. This M2 U2 you take to the other side. So you get over here, you get a factor of 2. Telling you that U1 minus U2 equals V2 minus V1. What is this thing telling you? Or in other words, let me write it in the opposite way. U2 minus U1 equals minus. Let me write it with a minus. U2 yeah, okay. What is this thing telling you? But what is this thing telling you physically? The relative velocity before the collision of the two objects equals in magnitude the relative velocity of the objects after the collision. The relative velocity of the objects after the collision is just opposite in direction. That's what this minus sign is telling you. U2 minus U1 is the relative velocity between the two objects before the collision. I mean, अगर ये जा रहा होता 60 kilometers per hour और ये जा रहा होता 120 kilometers per hour, what would you have told me for the relative velocity? 120 minus 60. इसलिए मैं कह रहा हूँ U2 minus U1 is the relative velocity. इसमें कोई इतने घूर के देखने की जरूरत नहीं है, okay? By exactly the same reason, V2 minus V1 is the relative velocity after the collision. Of course, I'm not bothering about relative velocity according to who of what, because I'm really interested in the magnitudes, okay? This is the relative velocity of object 2 according to 1, I think, okay? So you have that. And then it's flipped because of this minus sign, okay? Anyway, so this gives you the physical meaning that in an elastic collision, the relative velocity before the collision equals in magnitude the relative velocity after the collision. So what people do is, okay, ये है perfectly elastic collision के लिए. Let's say if you had a perfectly inelastic collision, what's the relative velocity after the collision? The two particles stick together for a perfectly inelastic collision. So they both move with the same velocity. What's the relative velocity then after the collision for an inelastic collision? 0. Because both particles after the collision are moving with the same velocity with respect to the ground. So with respect to each other, they are moving with the velocity 0. So therefore, वो कहते हैं realistic collision में इधर एक coefficient डाल देते हैं R, which tells you कि अगर R 1 है, then this is a perfectly elastic collision. अगर R 0 है, then you are dealing with essentially an inelastic collision. And this R is what is called the coefficient of restitution. Okay, essentially that's the idea behind the coefficient of restitution. In one of the problems in the readings, you look at this, okay, but anyway, not important, okay, over here, but I just wanted to point that out because किसी ने जिक्र किया था coefficient of restitution. It basically tells you essentially how elastic or how inelastic the collision is. For elastic collision, this equation is perfectly obeyed. If this is not perfectly obeyed, as in the right hand side becomes smaller than the left hand side, the coefficient of restitution takes into account how much smaller does it become. Okay. So anyway, now you have another equation. This is the product of, this takes into account conservation of kinetic energy. Therefore, it's much easier to solve this equation and this one. These are now both linear equations. You can solve these two simultaneously. It's much harder to solve these two simultaneously, but using these two, you can produce another linear equation and then solve the original original linear equation and this new second linear equation that you've derived. Okay. If you do that, then you first of all you say, okay, V2 from here, V2 is equal to U1 plus V1 minus U2. And then you plug this into your conservation of momentum equation and you get M1 U1 plus M2 U2 equals to M1 V1 plus you have M2 times V2 and you get U1 plus V1 minus U2. And remember, your objective now is to figure out V1. Then this equation does not contain V2, it only contains V1. So you just solve for that. So you get M1 U1 plus M2 U2 equals M1 V1 plus M2 U1 plus M2 V1 minus M2 U2. This M2 U2 you take to the other side. So you get over here, you get a factor of 2. M1 V1 इधर रहने दो, M2 U1 को दूसरी साइड पे ले जाओ. Minus M2 U1 and this equals basically M1 V1 and therefore this you can write as V1 times M1 plus M2 and you take this to the other side and you get that V1 equals this thing divided by M1 plus M2, but then you can tidy this up further because you can factor out M1 minus M2 from here. So if you do that, you get M1 minus M2, the magic of this thing, okay, U1 plus you get what? Well, not so magical after all, okay, but you get 2, आपके पास आ जाता है इधर M2 U2 minus 2 M2 U2. That's what you get. Again, algebra is not that important. It's straightforward algebra, okay? Nothing very magical over here. But what is important over here is to be able to make sure that this makes sense. So initially coin. So V1 is 0 and V2 is what? Ye 0 ho gaya dobara. This gives you 2 times M times U divided by 2 times M. So V2 is just U. Okay, and let's play around some more. और कौन से केस आपको आ रहे हैं ज़हन में जो obviously कोई elastic collision है and you kind of know the result. Well, suppose करो कि दो billiard balls एक दूसरे की तरफ आ रहे हैं with the same velocity u, with the same speed u. They don't have the same velocity, of course, because one is terminal. What happens after the collision? Without looking at those equations. Well, oh, bach gaya. They come in and then they just bounce back. So let's see. So over here you have that u1 equals u and u2 equals उन equations के मुताबिक u2 क्या होगा? When I derived all those equations, I assumed that u2 is the particle 2 is moving to the right. Now it's actually moving to the left, okay? That's why I said कि equation रट के ना जानते चले जाया करो. इसको रटने का literally zero फायदा है. सिर्फ equation रटोगे आपको कभी भी नहीं याद रहना इसमें assumption क्या built in थे. There was a huge assumption built in over here that I derived those equations under the assumption that all particles or both particles before the collision and after the collision are moving to the right. That's not, of course, always true. As you just saw, even before the collision over here, one of the particles could be moved to the left. But then you have to adjust that equation by saying, okay, u2 जो है वो negative होगा for this case. कौन सी equation? I mean, अगर मैंने f is equal to ma आपने लिख दिया, but वो formula sheet में भी लिखी होगी, so that's literally worthless. Okay, I mean you are basically done the same as a trained monkey. Okay, so उसका तो मैं कोई number नहीं देने. Okay. Okay, so you have u2 equals, इधर effort के मैंने marks नहीं देने, okay. So u2 equals, according to those equations, because in that equation it's as simple as, in that equation that is the direction of my coordinate axis. And remember, conservation of momentum is a vector equation. तो essentially देखो इधर मैंने, सर अब उस तरफ हो गया तो नेगेटिव कैसे मान गया? असल में तो ये चीज़ आपने इसके मुताबिक लिखी है ना. इसके मुताबिक जब लिखी है तो आप इस सिनेरियो में आप लिख रहे होते हैं m1 u1 ex minus m2 u2 ex. तो दिस माइनस को आप कंसीडर कर सकते हैं एज मल्टीप्लाइंग दिस u2. ओके, सो देन वी फिगर आउट कि भाई v1 क्या है. वेल m1 और m2 इक्वल हैं, सो दिस बिकम 0. दिस आई कैन जस्ट राइट एज 2m minus 2m u. क्योंकि ये u है और they are equal of equal mass, so I'm just taking the mass as m, minus 2m u divided by 2m, so you just get minus u. और इसको क्या हो रहा है? वेल इनिशियली ये तो जीरो हो जाता है, अगेन दैट्स एडवांटेज ऑफ हैविंग इक्वल मैसेज, एंड यू गेट 2m टाइम्स, ये हो जाता है आपका u1 आपका u है, 2m times u divided by 2m, you just get u, exactly as you expect. Another case कि एक छोटा सा पार्टिकल है एक of mass m that is colliding with a much bigger particle of mass capital M. इस केस में क्या होता है? I mean imagine you roll a ping pong towards a boulder, क्या होगा? The boulder will barely move if initially coin. So v1 is 0 and v2 is what? ये 0 हो गया दोबारा. This gives you 2 times m times u divided by 2 times m. So v2 is just u. Okay? And let's play around some more. और कौन से केस आपको आ रहे हैं ज़हन में जो obviously कोई elastic collision है and you kind of know the result. Well, suppose करो कि दो बिलियन बॉल्स एक दूसरे की तरफ आ रहे हैं with the same velocity u, with the same speed u. They don't have the same velocity, of course, because one is terminal. What happens after the collision? Without looking at those equations. Well, oh, बच गया. They come in and then they just bounce back. So let's see. So over here you have that u1 equals u and u2 equals उन equations के मुताबिक u2 क्या होगा? When I derived all those equations, I assumed that u2 is the particle 2 is moving to the right. Now it's actually moving to the left. Okay, that's why I said कि equation रट के ना जानते चले जाया करो. इसको रटने का literally zero फायदा है. सिर्फ equation रटोगे आपको कभी भी नहीं याद रहना इसमें assumption क्या built in थे. There was a huge assumption built in over here that I derived those equations under the assumption that all particles or both particles before the collision and after the collision are moving to the right. That's not of course always true. As you just saw, even before the collision over here, one of the particles could be moved to the left. But then you have to adjust that equation by saying कि भाई okay, u2 जो है वो negative होगा for this case. कौन सी equation? I mean अगर मैंने f is equal to ma आपने लिख दिया but वो formula sheet में भी लिखी होगी तो that's literally worthless. Okay, I mean you are basically done the same as a trained monkey. Okay, so उसका तो मैं कोई नंबर नहीं देने. Okay. Okay, so you have u2 equals इधर effort के मैंने marks नहीं देने. Okay. मैं ज़्यादातर usually to be honest मैं ज़्यादातर check नहीं करता because you know पहले check किया करता था but then I found कि मेरा IQ steadily decrease हो रहा है. So for the sanctity of my brain cells I stopped doing it. Okay. Now what I do is कि solution लिख देता हूँ और marking scheme भी पूरी बना देता हूँ and then you know but I do hold contestations. Contestation ज़्यादातर मैं खुद करता हूँ midterm और final के थे. Okay. So if you have any issue with the grading, मैं कहता हूँ कि मार्किंग स्कीम ले आओ, मुझे दिखाओ किधर मार्किंग स्कीम नहीं फॉलो हुई. अगर नहीं दिखा सके -1 तो सोच के आना कि वाकई यू हैव टू शो कि वाकई मार्किंग स्कीम नहीं फॉलो हुई. Okay. क्या चीज़? वो तो आपकी काबिलियत पे डिपेंड करता है ना. नहीं वो अगर मैंने बता दिया फिर आपके सीनियर्स के लिए रिस्पेक्ट खत्म हो जाएगी. सो मैं उनके लिए फॉर देयर सेक मैं नहीं बता सकता. ओके आपको इतने नखट्टू है ये. ओके नहीं ऑनेस्टली वैसे यू आर डूइंग मच बेटर देन योर सीनियर्स. ओके अंटिल हाँ सही कह रहा हूँ, सही कह रहा हूँ. I mean, if nothing else, वो एक कम से कम हनी बीज की आवाज नहीं आ रही मुझे हर वक्त क्लास में. ओके वो तो हर वक्त चुप ही नहीं करते थे. I mean, credit पे credit ड्यू. ओके भाई ये नहीं मतलब कि सर के शेखी में आप अगले 4 दिन कुछ पढ़ना ही ना. ओके कुछ पढ़ लेना. ओके सो एनीवे ऑल्दो पढ़ना नहीं चाहिए. ओके बट एनीवे ओके मतलब आई मीन टू बी फ्रैंक इसके आखिरी 4 दिनों में नहीं पढ़ना चाहिए, उससे पहले पढ़ लेना चाहिए था. ये नहीं कि अभी तक आपने नहीं पढ़ा तो अभी भी नहीं पढ़ो. ओके 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 सो एनीवे सो u2 equals according to those equations because in that equation is as simple as in that equation that is the direction of my coordinate axis and remember conservation momentum is a vector equation. तो essentially देखो इधर मैंने भाई सर अब उस तरफ हो गया तो नेगेटिव कैसे मान गया. असल में तो ये चीज आपने इसके मुताबिक लिखी है ना. इसके मुताबिक जब लिखिए तो आप इस सिनेरियो में आप लिख रहे होते m1 u1 ex minus m2 u2 ex. तो दिस माइनस को आप कंसीडर कर सकते हैं एज मल्टीप्लाइंग दिस u2. Okay, so then we figure out कि भाई v1 क्या है. Well, m1 और m2 equal हैं, so this becomes 0. This I can just write as 2m minus 2m u. क्योंकि ये u है और they are of equal mass, so I'm just taking the mass as m. Minus 2m u divided by 2m. So you just get minus u. और इसको क्या हो रहा है? Well, initially ये तो 0 हो जाता है. Again, that's the advantage of having equal masses. And you get 2m times, ये हो जाता है आपका u1 आपका u है. 2m times u divided by 2m, you just get u. Exactly as you expect. Another case, कि एक छोटा सा पार्टिकल है एक of mass m that is colliding with a much bigger particle of mass capital M. इस केस में क्या होता है? I mean, imagine you roll a ping pong towards a boulder. क्या होगा? The boulder will barely move, if at all. Of course, it depends on the size of the boulder, but linguistically, but in physics terms, that's not necessarily true. This could be, the force could be anything over here. Okay? And this, if you integrate the force over time, you get the change in momentum. Okay, so that is another way to understand how this conservation of momentum come about. If the external force is zero, what is delta P? 0, of course. The integral of 0 is, as you well know from the first page of your exams, the integral of 0 is 0. Okay? Right. So if you see the momentum of your system changing, look for some external force. You saw an example of that when we did the boat problem. जब मजनू जो छलांग मारी थी बीच पे और बीच पे आके रुक गया था, the momentum of the system changed. And then you looked around for an external force that caused that change in the linear momentum. हाँ. नहीं, इंटीग्रल अगर एक्सटर्नल फोर्स 0 है तो the integral of 0 is 0, right? ये क्या होगा? 0 plus 0 plus 0 plus 0. Never mind. ये definite integral है. In other words, okay, you are integrating from some initial time to some final time. Okay, इसमें कोई integration constant वगैरह नहीं आता. Okay. Right, so now let's do a prototypic example. Let's jump straight into a rocket. Next time around, we will do some more examples. Okay, let's jump straight to a rocket. Okay, so how does a rocket work? I just want to illustrate to you. अगली दफा कोड वगैरह भी दिखाऊंगा, simulations भी run करेंगे. Okay, to send you to the moon. Okay, how does a rocket work? नीचे क्या फेंकता है? कौन सी चीज फोर्स लगाती है रॉकेट पे? Obviously there should be a big upward force acting on the rocket so that the rocket picks up speed rapidly and eventually hopefully the speed of the rocket becomes bigger than the escape velocity of the earth and then you can go outside the influence of the earth. The question is, what is responsible for exerting this force on the rocket? नहीं, अर्थ तो यार, अर्थ तो उसको नीचे की तरफ खींच रही है, क्या हो गया है? इतना आसान होता तो मैं तो कब का चांद पे पहुंच चुका होता. So gases, कौन सी गैस ज्यादातर practically speaking? नहीं, बहुत कम. नहीं. Literally, steam. Most of the time, they basically there are two chambers, one with liquid hydrogen, one with liquid oxygen. It's about as primitive as you can get, okay? And then you make oxygen and hydrogen react together, and it produces water, but at high temperature, and high temperatures, what's water? Water is steam. And then you basically have to make the nozzle design, the escape mechanism for that gas in such a way कि very high pressure पे वो बड़ी तेजी से बाहर निकले. The faster the gases escape, you will see when we analyze this problem quantitatively, the bigger the acceleration of the rocket. So that's why these derivations are so important. ये आपको बताता है कि engineering point of view से कौन सी चीजें important है, कौन सी नहीं important. So when we do the carry out the analysis, you find out that the acceleration of the rocket sensitively depends on the escape velocity of these gases, the exhaust velocity, what is referred to. It also depends sensitively on how fast you pump out those gases. if you pump out 10 kg of steam every second, you get a much better acceleration of the rocket as compared to if you pumped out only 2 kg of steam every second. So, and then you can design your rocket all around that, okay? Acha. So, how do you analyze this rocket? So, a rocket works by essentially expelling out these gases. So, how do I work out the velocity of this rocket that is expelling out the gases at any instant of time? So, in other words, a rocket में जा रहा है. How do I figure out the velocity of the rocket at some time t? Just to make it general, इसको vector की form में लिख देते हैं. Okay. How do I do this? Believe it or not, the answer to this question is precisely that. That's what we will use. In other words, you just have to look at the rate of change of the momentum of this thing. But not just the rocket. क्योंकि rocket का तो mass change होता जा रहा है. The idea is to calculate this derivative. But this derivative, you have to calculate it very, very carefully. क्योंकि आपके different pieces of your system are traveling at different speeds. You don't have a speed of the system. In other words, system है क्या इधर? Remember, it goes back to the system. You have always, once you define your system, you have to stick to that definition. So at time t, it always works this way. If you have such a problem in which किसी चीज का mass change हो रहा है, the mass of the rocket is changing because it's burning some fuel, generating gases, and then it's pushing out those gases. So as time goes on, the mass of the rocket is decreasing. So the mass of the rocket is changing. So you cannot just consider the rocket alone as your system, because that goes back against what I just taught you, that the mass of the system cannot change. Once you have chosen your system, stick to that definition. So that means कि आपने time t पे एक snapshot लो, time t पे देखो situation क्या है. Time t पे rocket linguistically, but in physics terms that's not necessarily true. This could be, the force could be anything over here, okay? And this, if you integrate the force over time, you get the change in momentum. Okay, so that is another way to understand how this conservation of momentum come about. If the external force is zero, what is delta p? 0, of course. The integral of 0 is, as you well know from the first page of your exams, the integral of 0 is 0. Okay? Right. Delta t. Then I take the limit that delta t approaches 0 to give you that whatever you get should be equal to the external force. What you get is what is called the rocket equation. Okay? So let's do that, okay? So this is the situation at time t, this is the situation at time t plus delta t. What is the situation here? Mass थोड़ा सा change हो गया, so you have the initial mass plus the change in mass. Either of course आधी क्लास कहते हैं अस्तगफुरुल्लाह आपने rocket का mass increase कर दिया. No, delta m could be negative. This is now moving with a slightly different speed, hopefully, otherwise it's a very push rocket, okay? So you have v plus delta v. Delta v is a change in the velocity of the rocket. But I also have to include something else, because the mass of the system in the snapshot over here should be equal to the mass of the system in the snapshot over here. So और इधर मैं क्या चीज include कर लिया? The mass of the exhaust gases that have been expelled out. ये exhaust gases हैं, डब्बा, modeled as a box. So इनका mass क्या होगा? Minus delta m. Delta m itself is negative, so minus delta m is a positive number. You just want कि ये वाला mass plus ये वाला mass should be equal to capital M, not 0. Capital M उधर total mass है, तो इधर भी capital M ही आना चाहिए. हाँ. कौन सा? कर सकते हो, except that you're looking at a very small time difference. इसलिए आप emphasize करोगे वो essentially आप limit लोगे delta t approaches 0, then delta m also approaches 0, so delta m will become dm. इधर कई लोग m minus delta m करते हैं, फिर ये plus delta m होता है. कई लोग इधर m plus delta m करते हैं, फिर ये minus delta m होता है. Because delta m itself is negative. The change in the mass is negative, right? Okay. इसकी अब क्या velocity? Remember, you're doing the whole calculation, you'll do it in the frame of the ground. You cannot do it in the frame of the rocket. Why? Because in general, the rocket will be accelerating, hopefully. Okay? Otherwise, it's a very useless rocket. Okay, at least it's not sinking. But anyway, okay, so you'll do it in the frame of the ground. In the frame of the ground, आपकी gases जो आपने expel की उनकी क्या velocity है? Now, how do you know कि वो negative V होगी? I mean, it depends on the design of the rocket. It's the same way as कि भाई आप जिम में जाते हो, आप एक बॉल फेंकते हो. You say that okay, I have gained the ability to throw a ball with a speed of 10 meters per second. अब आप एक गाड़ी में बैठ जाते हो. What's the speed of the ball that you throw with respect to the ground now? सोच के बताना. Exactly. It depends on the speed of the car. I cannot give you a unique answer because I don't know the speed of the car. You can only throw it with a speed of 10 meters per second with respect to a frame in which you are stationary. But if you are in a moving car and then you threw the ball, if the car was moving at the speed of 20 meters per second and you threw the ball parallel to the motion of the car, the speed of the ball is 30 meters per second. If you threw it opposite to the motion of the car, then the speed is essentially smaller than that. आपने essentially kind of against the motion of the car फेंकी है. What engineers can set is the speed of the exhaust gases with respect to the rocket. Just like आप जिम जाके जो चीज़ आप कंट्रोल कर सकते हो, वो है speed of the ball with which you throw it with respect to the car. The speed with which you throw the ball with respect to the ground is dependent on the speed of the car. So the speed of the exhaust gases with respect to the rocket depends on the speed of the rocket. What you can control from engineering point of view is the speed of exhaust gases क्या है with respect to the rocket. So if you know the velocity of the rocket, of the exhaust gases with respect to the rocket. So you know the velocity of the exhaust gases with respect to the rocket. Stupid notation, इसको ज़्यादा तो लोग कहते हैं U. So U is the velocity, not the initial velocity. U is the velocity of the exhaust gases with respect to the rocket. The velocity of the rocket with respect to the ground in this snapshot is V plus delta V. तो लिखा हुआ है आपके सामने, okay? For those of you who couldn't figure it out, okay, use and do an eye test, okay? But anyway, and so now you know. So what's this velocity of the exhaust gases with respect to the ground? This thing plus this thing. Just like जैसे हमने ball जो है कार से फेंकते हैं, you add the two velocities. You don't need to worry about the directions क्योंकि ये vectors हैं. The directions will be built into them. So you have V plus delta V plus U. So the exhaust gases have velocity V plus delta V plus U. So then what do I have to do? I have to calculate the change in momentum. Change in momentum क्या होगा? ये minus ये. चलो ठीक है.